Okay, hello everyone. So let's start. Okay, okay. In the previous class, we had seen just a quick review about. We had started actually the sequential circuits. Okay, and we saw that this is basically based on this principle, by stability principle. Okay, and this is obtained by connecting two inverters back to back and feeding the output back to the input. Okay, so that forms a closed loop. Okay, and hence the input value is latched into this closed loop and is available uh, for a long duration of time. Okay, then this was the curve for this these two back to back connected inverters. Okay, and there were basically three uh, these are stable points, and the other points are called metastable points. So only we will operate the circuit only at these stable points. Okay, because only at these points the value will remain constant and it will not change by itself. Okay, then we but we wanted to add more inputs to uh, the this latch, because inverter could have only just one input signal. It cannot accommodate more than one input signal. So there is a need to add some more input signals so that we can have some more control uh, in the case we need to change the input signal or something else. Okay, if we need to add more than some more input signals also. Okay, so for satisfying those things, we have to use some other gates to construct the flip-flops, and this is a NOR gate based SR flip-flop. Okay, we saw this. Then this was the transistor implementation in terms of transistors. Okay, and it used around 1 2 3 6 7 8 number of transistors, the simple SR flip-flop. Okay, then we saw this multiplexer based latches. Okay, so the negative latch and the positive latch. The positive latch will operate will be in transparent mode when clock is 1, and will be in hold mode when clock is 0. Okay, and the operation for negative latch will be inverse, will be the reverse of what the positive latch operates. Okay, so the negative latch will be in transparent mode when clock is 0, and it will enter into hold mode when clock is 1. Okay, and this was the transistor level implementation. Okay, we saw this. And it can also be constructed using fast transistors. Okay, if there is a need to reduce power consumed, or and to reduce area by reducing the number of transistors used in constructing the circuit. Okay, so for reducing area, number of transistors and power, the same latch could also be implemented using some fast transistors. Okay, so this will now reduce the number of transistors. Here we had 1 2 3 4 5 6 7 8 9 10 number of transistors used, and here 1 2 3 4 5 6. So the number of transistors reduced from 10 to 6. Okay, so this is an advantage, but it also comes with certain disadvantages also, so beware of that. And for today's, let's start. uh, let's see this master slave as triggered register. Okay, so this consists of basically two stages. Okay, this is the master stage. This is the slave stage. Okay, and this is the timing diagram in the for this master slave register. So look at here. So when clock is 1, when clock is high here, okay, and let's assume any input signal that's coming at D. So this is the input signal that is entering into this register D. This is input, okay, and this QM is the output of the master, okay, which is here, master output, and this Q is the output of slave, or the whole complete master slave, and this Q is the final output, okay. So this is the final output, okay, which is this one, okay, and this is the intermediate output, we can say like this, okay, which is here, Q. So Q M for master, so master output, and this is the final output. So when clock is 1, so what will happen, let's see. When clock is 1, when clock is 1 here, when clock is 1, this 1 input, so this input signal will transfer to the output Q, and slave will be in transparent mode, okay. The slave is in transparent mode because the input signal present at QM, this node will transfer to the output Q here, okay. And when clock is 1 here, okay, this is active, this is not active, okay. Here in this case this was active, this was not active. So when this clock is 1, this is not active, hence the previous value of QM will be maintained, okay. Whatever value of QM was there, that was also fed back to this input, and that value will be maintained here under the condition when clock is 1. So it means that this master stage is in hold mode of operation, okay. So when clock is 1 here, look at here in the diagram, QM, this was in hold mode. So whatever previous value of QM was there, okay, that will be maintained here, and this is in hold mode. So this value is coming from the previous cycle, okay. And this slave is in transparent mode, okay, transparent mode. So whatever is the value of QM will get transferred to Q here directly, okay, because this connection is established right now, this connection is established. So the value of QM is getting directly transferred to Q. So look at here, the Q is getting transferred, QM value is getting transferred to Q, and this occurs when slave is in transparent mode, okay, under the condition when clock is high. So when clock goes low, when clock becomes 0 here, what happens? When clock becomes 0 here, okay, when clock becomes 0 the conditions will change, the operation of the master and slave stage both will change. So clock is going low here, clock is going low here, this becomes active, this non-active, this becomes active, and this inactive. So it means that this external input now can pass to the output of this master stage, and this enters into transparent, and this one will be in hold state, okay. So master is in transparent mode, okay, and QM will now start getting the value from D. So whatever is the value of D will get transferred to Q, okay, like this here. And since slave is in hold mode, okay, so the previous value of Q will be maintained, okay, the previous value of Q will be maintained here, and this is in hold mode, the slave is in hold mode, the previous value of Q is maintained like this, okay. Now let's see when again clock goes to 1. Okay, again clock goes to 1. When it is in 1, this is in hold mode, master is in hold mode, slave is in transparent mode. Okay, so QM master was in hold, is in hold mode, so the previous value of QM will be maintained here. Okay, the when clock is high, when clock is high here, this is in hold mode, the master stage, and this is in transparent mode. So what happens, the remember that before entering into hold mode it was in transparent mode. Okay, so it was getting the output from D. So before entering into hold mode it was in transparent mode. Okay, this was in transparent mode, so it was getting the output at that time from the external input D. So which value it will hold right now? It will hold the value which was last captured during when clock was low, during the time when clock was low. And when clock was low, this value of data D was captured. Okay, and this will be maintained here like this when it enters into hold mode. Okay, so this value will be repeated here under this condition for the master. And for the slave, which is in transparent mode now, so the value of QM will be transferring to Q directly. Okay, so the value of QM will be transferring to Q directly here. So it will look like this, similar. Okay, now again clock goes low, okay. So when clock is low, master is in transparent, so it will, the QM will follow D. Okay, so QM is now, has now started following D. Look at here. Okay, and this slave goes, enters into hold mode. Okay, enters into hold mode, so it will maintain the previous value of Q. So whatever previous value of Q was there, okay, that will be maintained here like this. Okay, so this is how the operation of this master slave register will take place. Okay, and when we look at the clock signal, the data and the final output, okay, what can we infer from here is that the output Q is changing when the clock signal is rising. Okay, so when clock signal is rising here and here, then the output is getting captured, the output is actually getting captured, the final output. Okay, and for the rest of the time, that is from here to here, for the rest of the complete cycle, the output remains same, from here to here, output value is maintained. Okay, again it captures a new value, the output, the Q captures a new value at the rising edge of the clock. Okay, and it maintains it for the rest of the cycle, it maintains the same value for the rest of the clock cycle. Okay, Now the thing is, what value is it capturing at rising edge? Okay, at this rising edge it is capturing the value of the input signal that is coming, that is entering into the circuit, that is this D, the external input D. At this rising edge the D value is this one, okay, and this is captured here and this remains here. At this rising edge the D value is this one, okay, this is captured and it is maintained here, okay. So this says that this master slave stage is a register or flip flop, okay, which is as triggered. So this is not a level trigger, this is actually edge triggered operation. Means the output is captured at the rising edge of the clock, and for the rest of the duration that particular value, that particular captured value is maintained, okay. Now it could have been other way around. We could have designed this so that the circuit captures the signal at the falling edge and it maintains for the rest of the time duration. So in that situation that thing can be achieved by interchanging this. So connect this positive latch here and this negative latch here, okay, just change their position and you will get a negative edge triggered master slave register, okay. And this is the transistor level implementation of the same circuit that we have just seen, okay. This is the master stage, okay, this is the slave stage right here, okay. We had seen this, this is actually the positive latch, okay, this is the negative latch, okay. So earlier it was represented in terms of block diagram, now it is in terms of transistor. So here basically this is transmission gate, this is second transmission gate, so this is third and this is fourth. So total of 4 transmission gates along with 1, 2, 3, 4, 5, 6 transistors are used here, okay. And one more inverters, and one more inverter is used here to form clock inversion, clock inverted signal, okay. So we can count the number of transistors used here for this circuit from this diagram. So 1, 2, 3, 4, 5, 6, 7, 8, then 2 for each inverter. So we have 1, 2, 3, 4, 5, 6, 7, 7 to the 14. So 14 plus 8, that becomes 22 number of transistors used here in this case, okay. Now there is a thing that if you want to reduce the number of transistors used here, you can implement this with another logic, that was fast transistor logic, okay. But again if you are using a different logic for getting some advantages, you should be aware of the disadvantage that it will that it carries with it, okay. So next we will start dynamic latches and registers. So let's see. So till then we had seen static latches and registers. Now this is about dynamic latch and registers, okay. So the difference between static and dynamic latches is that the static latches were constructed using the concept of feedback, okay, but here you will not see such feedbacking, but rather as we know that the dynamic circuits are based on the temporary storage of charge on the capacitors, okay. So it basically uses the charge stored on capacitors or those parasitic capacitors, okay, and the feedback concept is not used here. So you will see the circuits are or circuits are more simple. Circuits are simpler in the case of dynamic latches, okay. They will be simpler, they will be consuming less number of transistors, okay. but there are applications, there are specific applications for static latches and dynamic latches, static circuits and dynamic circuits, static and dynamic memories. Okay, so but there is an issue that the capacitor charges leaks with time, with time, because of the leakage currents and threshold currents. Okay, we know this thing. So if one wants to preserve signal integrity, okay, a periodic refresh of its value is necessary. So refreshment is to be provided for capacitors to retain their values, so that they can retain their values. Okay, and because of this phenomena, these are called as dynamic, dynamic storage or dynamic memories or dynamic circuits. Okay, and the reading the value of the stored signal from a capacitor without disrupting the charge requires a device with high impedance. So this is also a task that the capacitor is small and it will have a small charge content on this, and if we want to read the charge content, if we want to read the stored charge on the capacitor, whether it is a 0 or 1, whether it's high or low, then that should not disrupt, that should not change the charge content of the capacitor. Otherwise it will pose a problem, the capacitor charge will change. Okay, so it can be done, the reading from the capacitor charge can be done with the help of a device that should have a high impedance. Okay, otherwise when you don't provide a high impedance, then there is a chance that the capacitor charge may leak into the ground. Okay, so the device should be having a high impedance, then only proper reading from the capacitors would be done. Okay, so these are the points, some introductory points regarding dynamic memories. Okay, then okay, let's start with the first circuit, that is dynamic transmission gate as triggered registers. Okay, so look at this, these circuits are dynamic, so you can recognize whether the circuit is dynamic or static just by looking at the presence of capacitors. Okay, look at here, the capacitors are present, the parasitic capacitors are present, the C1, C2. Okay, and there is no feedback mechanism here, there is no feedback connection from output back to the input, no feedback. So you can recognize that this is a dynamic circuit, and this is basically a dynamic transmission gate, because it is using transmission gate as triggered register. Okay, this is the first transmission gate T1, this is the second transmission gate T2. Okay, and along with this two inverters are also used. Okay, I1 and this should be I2. So how will the circuit operate? And the transmission gates are controlled with clock signal. Okay, right, clock bar, clock. So let's see, when clock is 0, so when clock is 0, this clock bar becomes 1. Okay, this clock bar becomes 1, this clock is 0, right? So which transmission gate is active, is on? This one, T1, this, because a logic 0 at the gate of the PMOS will make this PMOS on, and a high input at the gate of NMOS will make this on. Okay, so basically this transistor T1 is on and this T2 will be off. That means that this path is not available. Okay, so this signal cannot pass to this node, But since this path is available, the value of D will pass to node 1, okay, and you will get at node 1 the value of D, and depending on the value of D, the capacitor will charge or discharge. Okay, if D is at high potential, the capacitor C1 will charge to VDD. Okay, if D is 0 ground, then capacitor this C1 will discharge to ground, or 0 it will hold 0 charge. Okay, so depending on the value of input signal D, the capacitor C1 will get its modified charge. It gets new charge. Okay, so you will get a 0 or 1 here at this node, right? And this is an inverter, so you will actually get D bar here at the output of this first inverter I1. Okay. Now, basically this inverter is a CMOS inverter. Okay, and we know that the CMOS circuits are an example of gate restoring circuit. Okay, so this does not this does not attenuate the value of input signals. If you are providing a 5 voltage here, you will get a 5 voltage here. If you are providing a 0, you will get a 0, proper 0. Okay. So because of this fact, inverter is inserted here. Okay, and this path was not available, so this D bar will remain here. Okay, this D bar will remain here when clock is 0, right? Now, when clock goes to 1, the clock bar will be 0, and this clock bar will be 0, and this clock 1. In this case, this T1 will be off, and this T2 will be on. This T2 will be conducting. This T1 will not be conducting. Okay, so the value of D, whatever value of D is there, if any new value at at this node comes, that will not affect the value of D here. Okay, so this D is the previous value of D, the value of D during the previous clock cycle. Okay, that is here. Now this T2 is available. Okay, the T2 is available. So this D bar value will pass through this transmission gate, and at node 2 you will get a value of D bar. Okay, and since this is an inverter, so this will invert this D bar, and you will get the value of Q as D here. Okay, so like this it will work for one half cycle. This stage, the first transmission gate will be active, on, and this second transmission gate will be off. Okay, and for the next half period of clock, the second transmission gate will be on, and this first transmission gate will be off. Okay, so what happens for first half cycle of the clock signal, that the first stage, the first transmission gate samples the input to this node. Okay, and for the second half of the clock cycle, the T2 samples this intermediate data to the final output node, that is Q. Okay, so this is how it will work, and it will be able to store the data at Q. Okay. Now for this circuit, the setup time, remember these timing metrics that we had defined some 1 or 2 classes back. Okay, so setup time was the time that was mm, required just before the actual capturing of the data. So when the clock is, suppose when we are working with a rising edge of the circuit, okay, then just before the rising edge, for in advance, for a certain duration of time, your data should be available, the stable data should be available. So if it is D, okay, so stable data, whatever value, should be available just before the actual capturing of the signal, actual capturing at the rising edge, okay. And this requirement was due to the setup time constraint, setup time. Okay, now if this circuit is a positive edge triggered register, okay, and the capturing will occur at the rising edge of the clock, okay, when the clock is changing from 0 to 1, the clock is changing from 0 to 1, okay, and the setup time of the circuit is simply the delay of the transmission gate and correspond to the time it takes node 1 to sample day input, the time it takes node 1 to sample the day input at node 1, okay, because when clock is changing from 0 to 1, so when it was 0, this transmission gate was on, okay, and D was coming here, and when it changed to 1, this transmission gate got off, okay, and this at this node maintained the previous input value. So capturing occurred during this transition, okay. So just before this rising edge, the stable data should be available. So and this is occurring here. So and the input to this circuit is this D. The input should be available just before the rising edge of the clock. Okay, so this suggests that the setup time for this circuit would be the delay of this transmission gate T1, okay, and which is actually the time that the signal takes to be sampled at node 1, at node 1. So at node 1 you will get the value of setup time, that is TSU, okay. Now when the clock changes from 0 to 1, okay, after this also, since the task is complete, but still the circuit, there is a requirement constraint that after this capturing has occurred, again the data should remain valid for a certain duration of time, okay, and this constraint was given by T hold time, and the hold time is approximately 0 here, okay, since the transmission gate is turned off on the clock edge and further inputs changes are ignored. So when clock changes from 0 to 1, this transmission gate turns off, and any changes in the external input isn't going to affect this node signal. So and because of this, the hold time for this circuit would be approximately 0, okay. The propagation delay TCQ is equal to the two inverter delays plus the delay of transmission gate T2. So from here the propagation delay will be the delay of two inverters, this one plus the delay of the transmission gate T2, that is this one, okay. Okay, so we will end here for this class, and then we will resume from here in the next class, right?